Alright, this is page 47 of the Incredibles book. I know this is starting like in the middle of the process. You have already seen some of this. So what I'm going to do is just start here and start with just the plug it in rules, right? I had already discussed this before. The idea is when you take a limit, your goal is to really just get it to the point where you can plug it in and find the limit. So here's a good example. What is the tangent of pi? It's 0, so that is also the limit. Okay. What is the cosine of 0? Cosine of 0 is 1. Square that, and it's still 1. Right? So it's 1 squared, so that's just 1. Here, plug in 0. Sine of 0 is 0. E to the 0 is 1. So 0 over 1 is 0. Here, plug in e. That's going to be natural log of e squared, which is just 2. If you don't know that, ask me. All right, plug in -1. If you plug in -1, it's going to be -1 squared, e to the -1. So that's 1 over e. All right, and cosecant of 5 pi over 6. Cosecant of 5 pi over 6. That's same as 1 over sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. So this is 1 over 1/2. So that's just 2. All right, that's it. Okay, so your goal is to be able to plug it in, but what happens if it fails to plug in? What happens when it fails to plug in? Now, what does it mean? What does it look like to fail to plug in? All right, so we're going to look at number 4. Okay, so I think this is where you have seen these problems before, but let's plug it in. So if I plug in -3, that's going to be -3 squared, which is 9, plus a -3, or just -3, minus 6. So all I've done is plug it into the numerator. If I plug in -3 into the numerator, that becomes 0. If I plug in the denominator, that also becomes 0, right? -3 plus 3 is 0. So what I have is a 0 over 0 form. That's when it fails, okay? Now, there are more than one way to fail. This is a way to fail where it might be fixable, okay? There is a hole in the graph, and you might be able to fix it. All right, and that's what this idea is, right? Functions that agree at all but one point and fill the hole. So what we're going to do is try to fill this hole. All right, now, to do that, we're going to do some algebra. Is this blurry? Try to focus it. All right. So what I'm going to do, so I am now just rewriting the limit, but I'm going to do some algebra and factor that out. So I'm going to factor the numerator. That's going to be x plus 3 times x minus 2 all over x plus 3. So the x plus 3's reduce, leaving you x minus 2. Now you can plug it in. So that's -5. So as a result, the final answer is -5. So the limit is -5. So our goal is to mess with it so that we can plug it in. And that's what happened. So when we finally got it, so this is these two, x minus 2 and the original form, are equivalent except that x equals -3. That's it. All right, let's continue with b. So I'm going to factor the numerator, which would be x minus 1, x plus 1. It's a difference of 2 squares. Right, reduce the x minus 1's, and you just have x plus 1. Now plug in the 1, and you get 2. Oh, one thing I forgot to do is check to see what happens when I plug in the 1. When I plug in the 1, it's 1 squared minus 1, which is 0. Plug in the 1 in the denominator, it's 1 minus 1 is 0. Okay, so it was correct to do what I did. Okay, so you should plug it in to see if you actually have what's called an indeterminate form. So 0 over 0 is an indeterminate form. All right, that's it. Okay, all right, let's rationalize the numerator. Okay, so you've heard about rationalize the denominator. You can actually rationalize whatever you want. Okay, so here, in this case, we're going to rationalize the numerator. So you're going to multiply the numerator by the conjugate of that expression. The conjugate of that expression is square root of x plus 1. So I'm keeping the first part, changing the sign, plus then the second part. Right? This is all based on this idea, a minus b times a plus b. Right? When you multiply that out, that's a squared minus b squared. Okay, that's an old Algebra 1 idea, which was also covered in Geometry and Algebra 2. Now, if you multiply the numerator by that, you also have to multiply the denominator by that. So that's what I'm doing. All right, so now we're going to do some algebra here, work it out. So you multiplying square root of x plus 1 times square root of x plus 1. So it's square root of x plus 1 squared minus 1 squared. All I'm doing is copying the denominator. All right. By the way, if you skip this step, that's great. That means you know this thing, right? So if you have this instead, if you go straight to this, so if you go from here to here, that is perfectly okay, right? Because the whole point was to get rid of that radical, all right? Now simplify this. 1 minus 1 is 0. So I have x in the numerator and x square root of x plus 1. Sorry, it's going to get scroungy there. All right, continuing. So the x is reduced. So there's an x in the numerator and x in the denominator that can reduce. So I'm going to reduce those two. So that's 1 over the square root of x plus 1 plus 1. All right, now someone asked, how do you know when to stop? Well, the idea was to get rid of whatever is causing the 0 in the denominator, okay? So basically, if something from the numerator and denominator reduces, it's probably a good time to check to see if you can stop, all right? So I'm going to plug in the 0 here. If I plug in the 0, what I have is square root of 1 plus 1. Now at this point, since I'm able to plug it in, I have no longer a need to write the limit sign because I've taken the limit. Square root of 1 is 1, so it's 1 plus 1 in the denominator, so it's 1/2. That is the answer. You can skip several of these steps. You can definitely skip this one and go straight into this one, okay? And some people may see that they can go straight to this one. And then, all right, that's it. Don't skip too many steps. So it's very easy to make a mistake if you skip steps on this. All right, so you saw one where I had to rationalize the numerator. Now, so what am I going to do when I have a complex fraction like this? Well, let's plug in, make sure we have to do anything. So if I plug in 0 here, that's be 1/3. So it's 1/3 minus 1/3 is 0. Plug 0 in the denominator and I have 0. So I have the indeterminate form 0 over 0. All right, I shouldn't have written that. All right, so what I'm going to do to fix this is to multiply the numerator by the common denominator. So the common denominator here is 3 times x plus 3. So I'm going to multiply the numerator and denominator by that. Remember, so if I multiply the numerator and denominator by the same thing, I have not, algebraically speaking, changed the problem. Okay? This is a 1. This is a fancy form of a 1. All right. Now, what I'm going to do now is multiply, and I'm going to do some work on the side to make sure you understand what's going on. So I'm going to write over here 1 over x plus 3 minus 1/3. And you're taking this 3 times x plus 3 and you're multiplying each term of that difference. So I'm multiplying by 3 times x plus 3 and 3 times x plus 3. So this is side work to show you what's going on. A lot of people get confused right here. So if I multiply here, the x plus 3's cancel, and I'm left with, all right, let me work this out. So this is leaving a 3. 1 times 3 is 3. So there's a 3 here. And the 3's cancel here. And that's left with x plus 3. Excuse me. Over. Now in the denominator, nothing interesting is happening. So I'm just going to rearrange 3 in the x. So it's 3x times x plus 3. Sorry about that. Okay. Now, some warning. Some people think, oh, I can cancel x plus 3. No, you cannot cancel those two because of that minus sign. Okay? Unless this is a multiplication sign, you cannot cancel that x plus 3. If it's a minus sign or plus sign attached to something, it cannot be canceled. Continue. All right, so now I'm going to distribute the minus sign, so it's minus x minus 3. And 3 minus 3 is 0. Okay, so I'm going up here. Oh, I'm running out of space. So that means it's negative x over 3x, x plus 3. Right? So the x is reduced. So that's negative 1 in the numerator. And the x's are gone, so just x plus 3 in the denominator. And that's a 0. Now plug in the 0. 0 plus 3 is 3. So that means final answer is negative 1/9. Right? 3 times 3 is 9. That's it. Okay, number 7, there is not enough room there. So I'm going to do that on separate paper. This is a sign of things to come. This is number 7, limit as h goes to 0. I'm just copying the problem. I hope I don't make a mistake copying the problem. All right, some of the biggest confusion here is they look at this, well, there's 2 letters. Does that mean there's 2 variables? And the answer is no. Okay, in this limit, the h is the variable because of this. Because it's listed here, h is the variable. So that means x is treated like a number, treated as a constant. Okay, so it doesn't change, so x doesn't change. So it's only h that's changing. Okay, now we're going to do some algebra to, what's the word? To expand and simplify. So I'm going to have to actually square x plus h. So that's x squared plus 2xh plus h squared. So I've taken x plus h squared, that's same as x plus h times x plus h. Work that out, and that's what you get. All right? Now we'll distribute that, so it's minus 3x minus 3h, and I'm just copying the rest. Plus 2 minus 4x squared plus 3x minus 2 all over h. Okay, so let's see what we got here. So I have a negative 3x and a positive 3x, that cancels. I have a 2 minus 2, that cancels. Okay, well, not much else canceled. I'm going to go ahead and distribute that 4 now. I'm distributing the 4. So that's 4x squared plus 8xh plus 4h squared minus 3h minus 4x squared. Right? I'm making sure to write down everything I didn't cancel. And now I have more canceling. 4x squared minus 4x squared cancel. And all those things have an h in them. So that's 8xh plus 4h squared minus 3h over h. Now, there's a common factor of h, so let's go ahead and take that out. So I take an h out, so it's 8x plus 4h minus 3 over h. Okay, all right, now, so the h is reduced. And now I can plug in the 0. If I plug in the 0, the 4h, 4 times 0 is 0, so that just basically goes away. So the final answer is 8x minus 3. That's it. That's number 7. This is a long, arduous process. It's not particularly difficult. It's just long and, well, boring. All right? But this is something you're going to have to get used to for Chapter 2. So it's not a big part of Chapter 1, but it is a huge part of Chapter 2. All right, so final answer for number 7 is 8x minus 3. Let's look at number 8. Okay, number 8 is actually easy, okay? So let's kind of talk about what's going on here. So here we're asking the question, limit as x approaches 2 of f of x. That's the question, Okay, it's kind of hard to see with all that information, but this is really what the question is. What is that limit? Now, the weird part is 2, the one you're looking at, is in the boundary. And remember, whenever it's written like this, we're looking for a two-sided limit. So what's going on from the left and what's going on from the right? Well, it's pretty easy. Well, to find the left side, in other words, numbers that are less than 2, we can plug the 2 into here. If you plug the 2 into there, the 2 times 5 is 10, plus 2 is 12. Okay, so that 12 is essentially this. Limit as x approaches 2 from the left of f of x is 12. Now, plug in the 2 into the top part. Right? If you plug in the top part, that's going to be 3 times 4 is 12, minus 1 is 11. So what I've done just now is found the limit from the right. So from the left, the limit is 12. From the right, the limit is 11. Remember, we don't care what actually happens at 2, but our goal is to be able to just plug it in. So that works. So we don't care that the 2 is on both of them, or actually one of them, but not the other. But remember, we're looking at behavior. Where is it going? So to find out where it's going, we just plug in the number. All right. Now, so we have a left-hand limit of 12. We have a right-hand limit of 11. They do not agree with each other, so that means it looks something like what? So from 2, so if it's 2, it's going up to 12 from this side and 11 from this side. So it is one of those broken things, so the limit does not exist. Remember, when the left-hand limit and the right-hand limit do not agree with each other, we say the limit does not exist. All right, almost done. Okay, I know this is a long video, sorry. Okay, they go on and on about Squeeze Theorem, and they say use the Squeeze Theorem. These are not really called Squeeze Theorem. You use the Squeeze Theorem to prove it, okay? But basically, you are expected to know these, memorize these, okay? So here, the limit of this, sine x over x equals 1. You might think, okay, what happens when I plug it in? What happens when I plug in 0? You get 0 over 0. That's an indeterminate form. But here's the bad news. I don't have any algebra to simplify that. But I'm just telling you the answer is 1. And it doesn't matter which way it's facing, right? The reciprocal of the limit is still 1. Over here, by the way, there will be something I will teach you at a later date. And maybe that's a week away, maybe it's 2 weeks away. But it's not too far away, where I will show you an easy way if you can't remember this. No, you just need to remember this. All right, so here, the limit here is 0. And here, you cannot flip it upside down. However, you can change the order of the subtraction and still get a limit of 0. Okay, and in this one, the limit is e. E is approximately 2.71 something, right? This is like pi. It's one of those transcendental numbers, I guess. All right, but that's what e is. Okay, so what do I do with this tangent x? Well, rewrite it as sine and cosine. So that's going to be sine x over cosine x over x. Now, I'm going to do some algebra, not trig, but some algebra. So that was a trig step because I changed the tangent x to sine x and cosine. Now I'm going to do some algebra steps, and I'm just going to rewrite this. So I have an x in the denominator, and so I have a fraction and a fraction. So I'm going to rewrite this as a product. So instead of division, it's a product, and those are equivalent. If you don't remember your algebra skills, just please let me know. Now, what I want to do is more algebra. And the goal here is to make it look like something I know. Well, I have sine x over x. So that means that if I swap these two, remember, multiplication is commutative. So that means I can swap the x and cosine. Okay? This I know the limit of. This approaches 1. What happens to 1 over cosine x? So remember, our goal is just plug it in. So we'll plug it into 0. Cosine of 0, if you don't remember, is 1. So this is approaching 1. So it's 1 times 1, so the limit is 1. That's it. Okay? All right. Looking at B. So I'm going to do B twice. And I have to do it twice because I'm going to do it the long way the first time and then a short way the second time. All right. So I'm going to write this on separate paper so that you can see the two different ways. And you will want to, if you want to skip the first way, that's fine, because you're going to be doing it the second way every time. So all I'm doing now is copying the problem. Okay. Now, what I didn't mention earlier is that for this limit to work, this angle, the angle that's inside a sine, and the denominator, they have to be identical. Well, this is not identical. Well, here's the weird part, though. I could just throw a 4 down there. And you think, well, now I've changed the problem. Well, that's true. So if I put a 4 in the denominator, I have to put a 4 in the numerator. Okay? So I've multiplied by 1 in the form of 4 over 4. Okay? However, this part right here, I know the limit of. That's 1. What's the limit of 4 as x goes to 0? Well, the limit of 4 as x goes to 0 is 4. So what I have here, that part's going to 4, and then this combination is going to 1. So it's 4 times 1, or 4. And you might think, well, that's easy enough. Well, it's true. If you want to do it this way, that's fine. The second way is to realize, well, you can just look at the ratio of what I have here. I have 4 here. When I say look at the ratio, I'm looking at the ratio of this part right here. Technically, that's not, okay, it's not a ratio. Okay, but just look at the 4x over x, right? So it's just 4 over 1, so just 4. So this trick works every time. You can just say the limit is 4. Okay, that way you don't have to do this gobbledygook of multiplying the denominator and numerator by 4. However, if you just want to, that's okay. All right, final example, C. So that was the second method. Just look at the ratio of the angles you have. And this works even if they're upside down. If I have x goes to 0 and I have, say, 3x over sine of 4x, I could just look at the ratio, it's just 3/4. And that's the answer. Okay, that's it. All right, C. C doesn't have any multiple methods. I'm just going to write it out. So 1 minus cosine squared x, I don't have a square on these, so I have to factor this. So it's going to be 1 minus cosine x times 1 plus cosine x over x. All right, so I could just put it here. I could put the x over here. Okay, and what is the limit of this? Well, that's this one right here. The limit of that is 0. And you want to make sure that this limit exists. So cosine of 0 is 1, so this is going to 2, because 1 plus 1 makes 2. All right, so that means it's 0 times 2, or 0. And that's the answer. And that's the last example. And I'm done for today. All right.